So in this question here, we've got some data and it produces an exponential model. So the time compared to the variable n. Time is the independent variable, n is the dependent variable. So what we got when it was graphed was something that looked a little bit like that curve. Now what we wanted to do was try and code the data to try and make some sort of linear representation of that data. So we used log base 10 of n. And they're the values we got, and they are approximate values. So we didn't use too many decimal places because we just wanted to see what would happen on the graph. And that gave us a line, something like that. And then with the marks reasonably close with quite a high correlation. So that was a valid linear representation of the data after coding it. And we used y equals log base 10 of y, and we used x equals x. So we now want to find the new linear model of that linear representation. Now the linear representation, what we found was y is approximately 2.71 minus 0.352x. And that would seem reasonable because as n went to 0, that would probably end up at about 2.71, and it's got a negative gradient that was reasonably around a third. So that looks good for that so far. Now what we're going to do is find the new linear model using this information and this coding. So as log base 10 of y is the new y and x equals x, we can rewrite this. So we've got log base 10 of y. Let's set it to equals because we want to use it to estimate values. And we got 2.71, so 2.71 minus 0.352x. So that's as it was there because the coding on the right hand side of the equation is just x equals x. So now we're going to try and do is get the y on its own. So to do that, as we've got log base 10, we'll raise everything to the base 10. So now I've got 10 to the log base 10 of y equals 10 to the 2.71 minus 0.35, sorry, 3, let's put that there, 352x. Okay, now we can simplify. That's why we raised it to the base of 10. 10 to the log of 10 just cancels out and we leave ourselves with y. So y equals that. And this one, by the laws of indices, we can break this apart. So 10 to the 2.71 times 10 to the minus 0.352x. Okay, now this one we can plug in our calculator and you'll get approximately 512. So we can deal with that straight away. This one we need to be a little bit more careful. Now what I could rewrite this is 10 to the minus 0.352. So open that up in brackets, minus 0.352, and then raise that to the power of x. And then we can plug that into our calculator and get a value and then rewrite it in terms of the indice x. So then we get y equals 512 times, now this will give you approximately 0.44. So that's 0.44 to the power of x. And then that then will give us a chance to estimate some values along this linear representation. So that is the linear representation after we've coded our data, log base 10. And then you can try some values and you'll get some reasonably close, but again this is going to be only an estimation, but it's certainly easier to use than on the exponential curve. Okay.